Our lecture 6 of VLSI Design Theory, and today we'll be starting off with the physical operation of a MOSFET, also known as the working principle of it. Okay, so this is our device structure as you can see in your screen. So we have already discussed about this, so we are going to continue from that point. All right, now when you look at this device structure of an nMOS of enhancement type, what we see is that the substrate is P type and there are two N plus pockets in the slab, the semiconductor slab, right? This is our oxide, this is our metal. Okay, so that's the first thing that we can notice, that we have a substrate of P type and two N plus pockets at the surface of the semiconductor, isn't it? So now what I'm pointing at is, normally the substrate forms two PN junctions with the N plus pockets of source and drain regions. This is our observation. Okay, so this is our source N plus region and this is our drain N plus region, and this is our substrate, and the three of them together will look like two PN junctions. How? This is one PN junction, this is another PN junction. Okay, so the plus over here is because it is highly doped, so that won't matter, it will still be named as a PN junction. So there are two back to back PN junctions that we have in our device structure. All right, so this is our first observation. Second observation is that, see, whenever you will see an actual MOSFET that you will use in your breadboard that you will be using, if you are in like third sem or you are in the analog lab. So this is how the MOSFET will look like. You will only see 3 pins, but we have discussed that a MOSFET is 4 terminal, and in the device structure also we can see it is a 4 terminal device. Then why the actual MOSFET that you will be using in your analog labs has only 3 pins? That is a big question, isn't it? Suddenly one terminal cannot be just poof in the air. It cannot go poof in the air, isn't it? It can't vanish. So basically, since we are forming this back to back PN junctions within our substrate itself, what happens is, drain terminal will be relatively positive in comparison to source, because drain is the terminal where we will be applying the voltage. Okay, so what happens is, so that means what, if we are applying the voltage at drain, there has to be some grounding. So that grounding part or negative voltage part will be the source terminal. Okay, so two things, it can be grounded directly. Whenever I am saying grounding, that means grounded directly means 0 volts. Okay, or if it is a negative voltage that we will be giving, so it will be some negative voltage like -5, -9, -1, so on and so forth. Okay, so that is what I'm saying, that either by this statement, that drain is relatively positive in comparison to source. That means we are going to give the input voltage over here at the drain terminal, and the source will either be grounded or will be applying some negative voltages to it. So when we are doing this, we can easily, so this will be for when we are putting this, the body terminal will be connected to source terminal. So whatever we are giving, either 0 volts or some negative voltage, that same thing will be connected to our body terminal. By doing that, what we will achieve is that body will have no effect on the MOSFET. Body will have no effect on the MOSFET, and since its effect will be cancelled out the moment you connect it to the source of the same MOSFET, what will happen is you will get this 3-terminal thing in your analog lab. Okay, so never get confused that you're studying it's a 4-terminal device, but when you're going into the lab of analog electronics and you see that the MOSFET is a 3-terminal pin, you might get confused. So this is how we are getting that 3-terminal activity of a MOSFET, but in actuality a MOSFET is always a 4-terminal device. So this question is also going to, like in likelihood of your viva, will become a part of your viva question, and most of the students of 6th sem might get confused. Okay, that in theory we have learned that it's a 4-terminal device, and suddenly your professor will take out that MOSFET IC and you will see only 3 terminals, then you might lose your marks. So pay attention to that. Okay, now apart from that, so this is what we have achieved so far. Now at the beginning of, like when I was introducing you the MOSFET, at the beginning of it, like why BJT, why not MOSFET and all those things, I had mentioned that a MOSFET is a voltage controlled device. Remember, it was one of the points. Voltage controlled device. That means the whole operation of a MOSFET will be controlled via some kind of a voltage from some of the terminals. Now I have got how many terminals? 4 terminals. Now in which which terminal out of this 4 will act as the controller? Will it be the drain? Will it be the source? Or will it be body or gate? See, I have already just now I have told you that drain will be comparatively positive in comparison to our source, and we will cancel out the effect of body by connecting it to the source. So these two, source and body terminals, are already out of the league. What about drain? Drain is also out of the league. It is for our input voltage. Okay, so what is the terminal left with us? That is gate. So gate is the terminal which will act as the controller of the whole MOSFET. Now what do you understand by this term, that controller of the whole MOSFET? Basically whenever we say that it's a voltage controlled device and everything, and gate is that terminal, means gate terminal will act as the switch of this MOSFET. That means by giving an appropriate voltage, I can either turn the MOSFET on or turn it off. Okay, so that is what we mean by this. Okay, now another point that you have to remember, okay, that is source and drain are interchangeable. Source and drain terminals are interchangeable. You can already see it in this diagram itself, isn't it? Both are same to each other. So I can actually interchange drain and source and still my device will function the same. Okay? And since it is interchangeable, so MOSFET becomes a symmetrical device. MOSFET becomes a symmetrical device. So these are all our observations that we need to remember. Okay. So now, before we start the physical operation, another point, that we have got another name for our MOSFET, It is also called IGFET. So FET full form remains the same. IG means, or IG stands for insulated gate. And when we are discussing the whole physical operation, you will understand why am I saying this. Okay, so now let's begin. Okay, so the first step is that no voltage is applied, okay, so that means what? No gate voltage. Just now I told you that gate is our terminal that will be controlling our device. Okay, so either we can turn it on or turn it off. So if I'm not providing any gate voltage, that means what? It is not going to function. So no VGS is given. That means what? What will be the outcome of this? That there will be two PN junctions, or PN junctions are also known as diodes. So there will be, since I'm not giving any kind of voltages, so there will be two reverse biased PN junctions or diodes exists in series. So this n plus and p. Okay, so this is our one junction, this is our second junction, and since we are not providing any kind of voltage, so what will happen? It will be in a reverse bias condition, and that too in series. Okay, so it will look something like this. Okay, it is in series connection. Since I have got two reverse biased diodes in series, what will happen? Will we have any kind of conductivity? Of course not. We will have no conductivity whatsoever. So no conductivity. No conductivity means what? No current. No current means what is the outcome, or what is the conclusion we can draw from here? That very high resistance is present. If there is no current means what? Too much resistance is there. If it is having too much resistance, that means what? It is going to give us, the range is 10 to the power of 12 ohms. It is too huge, so there will be no conductivity. So the first step of our physical operation is no voltage is applied, and when we are applying no voltage, what will happen? That we have discussed. Okay, so till this point there is no conductivity, there is nothing is going to happen over here. So till now we haven't started. Okay, now let us start this. Let us turn on the MOSFET. Okay, let us turn on the MOSFET. How we will do so? Let's see. So now see, the second step is named as creating a channel. You remember in our previous class we had shown you that this was our MOSFET, and within this I had shown you that it will be looking like a thin rectangular connection between the two N plus pockets. So it is not, it does not come manufactured within the MOSFET. You have to give certain amount of voltage and certain amount of conditions you have to comply by, and then this channel will form. Okay, so it does not come pre-made inside the MOSFET. Okay, so how we will create a channel? Now in this diagram you can see that I have already drawn from the beginning. These are my 4 terminals, and source is grounded, drain is grounded, body is also grounded. What is not grounded? My gate terminal. Okay, now I will be looking from the source side. Why will I be looking from the source side? Why not drain? You only said na SSG that both drain and source are interchangeable. Then why am I looking from source? Because at one point of time drain will have some positive voltage to it. Okay, some kind of voltage will be provided, but source is always going to be grounded. So whenever we look from the source and there is some kind of voltage in the ground, what will be the name of our voltage then? It will be termed as VGS. That means voltage in the gate terminal and source is grounded. Okay, so that is how all our voltages will be named. Okay, that is how all our voltages will be named. So I have given voltage to my gate. Okay, so what kind of voltage? In this also we will have some steps. Okay, first, a small negative voltage at gate. A small negative voltage at gate. So if I am giving a negative voltage at gate, okay, now gate is on top of this p-type substrate, isn't it? Now p-type substrate, okay, so p-type substrate means what? Majority carriers will be there and minority carriers will also be there. What is the majority carrier of p-type? Holes. What is the minority carrier of p-type? Electrons. Okay, now, and while we are at this, what will be the majority and minority of n plus regions? Majority will be electrons and minority will be holes. Okay, so this you have to remember. So when I am providing a negative voltage at the gate, what will happen? The majority carriers, when I am giving negative voltage at my gate, the holes from the p-type substrate, what will happen to them? They will be attracted towards the surface. They will be attracted towards the surface. And what will happen? They will be nearing this portion, isn't it? So all the holes will get attracted towards the surface of the substrate. Now when that happens, what will we say? That the holes from the bulk, or bulk means what? This is my p-type substrate. This portion I am saying that it is the surface. So the rest part will be termed as bulk. Okay. So holes from the bulk accumulate at the surface. Okay, accumulate at the surface. All right. Then, so we have gathered the holes from the bulk of the p-type semiconductor towards the surface. Okay. Now, what I will do is, after I have achieved this, I will now make changes to my voltage at gate. Why? Why will I do that? Because our MOSFET is a voltage control device, so I have to see what happens at different levels of our voltages. Okay, so a small positive voltage at gate. Okay, small positive voltage at gate. So now at this point, before I apply the positive voltage at gate, okay, Till that point I have got the holes covering my surface. Okay. So now the moment I apply positive voltage, what will happen? All the holes that were gathered over here, now electrons are negative in nature, holes are positive. What will happen? Positive, what will happen? It will repel. So with the moment I apply the small positive voltage at gate, it will repel the accumulated holes at the surface and make them move back to the bulk. Okay, so the moment I apply the positive voltage, what is happening? All the accumulated holes were here at the surface. This is positive, what will happen? Repulsion. And when it is getting repulsed, it is means what? All the holes are made to move at the bulk of my substrate. Now what happens when the carriers are repelled back? There will be a void, isn't it? Because at this point of time and at this particular voltage that we have provided at the gate, I have repelled them back, I have repelled the charges back. So at this point it will have no carriers, so it will be a void, and this at this portion there will be no carriers left. Okay, no carriers left. So this has happened because I have given a small positive voltage at gate. Okay, now third point, let's see if I increase this positive voltage, then what will happen? So increasing the positive voltage at gate, what will happen? Let's see. Increased positive voltage at gate. Okay, so now when I had given a small positive voltage at gate, what happened? It repelled the majority holes into the bulk, and by doing so, what we got? We got a void. Between our two n plus regions. Now I have simply increased the positive voltage that we had given at VGS. Okay, now let's see what happens now. Now the moment I have done this, so what will happen? Will the holes move towards the surface? Of course not. It is like at the small positive voltage only it had repelled all those holes. Then if I am increasing the quantity of my positive voltage, what will happen? I had already told you that the p types, it is a semiconductor, it will have both majority and minority. Now the minority carriers that were way back into the bulk of our p type, okay, very small quantity of them, what will happen if I keep on increasing the positive gate voltage? What will happen? These negative or the electrons that form the minority carriers of my p type will get attracted towards this void. Okay, and when that happens, can you see this n plus regions also? N plus region is what? Like it is the majority carriers are electrons, and since it is highly doped, it will have more number of electrons. Okay, so at this increased positive gate voltage, the electrons from the n plus type on both the sides will also get attracted, towards this void. So if I keep on increasing the positive voltage at gate, the electrons from the p type and from the n plus pockets will get attracted towards the surface of the substrate. Okay, so now we had a void over here, isn't it? We had a void, and apart from the holes, the p-type substrate also has some minority carriers also. So these are those minority carriers, and since we also have highly doped regions of n plus, that means more number of electrons are there as majority. So electrons from here, both the sides, and all these electrons that are the minority charge carriers of our p-type will move towards the surface in this void that we had already got. Okay, so now this void, will it remain a void? No, it will be having what? It will be having electrons instead of void. Okay, now what will be my structure that look like? So we will have this n plus and p-type like this, and over here all the electrons that will get attracted from the n plus regions and the bulk will come and get accumulated at this region. Okay, so can you observe? Let us observe something over here. This is what? p-type. Okay, this is my bulk. Okay, let's not call it a bulk right now. We have the substrate as p-type, and the surface of my substrate is having what? Electrons. So majority should have been holes, but my surface is having electrons. So that means what? Because of this, by keeping on increasing our positive voltage at gate, what has happened? The surface of p-type semiconductor has inverted. It's against its nature, right? It's against its nature, and the surface has inverted. So instead of having holes, it is now giving you electrons. Okay, now this electrons that has caused the surface to invert, okay, so our surface has inverted. Okay, and all the electrons are in this region. So n plus regions are also electrons, and this is also electron. So now if I can say that this thing is connecting the n plus pockets, it's acting like a bridge. So this is nothing but our channel. So by doing this, we have created our channel. Okay, and this step that we discussed, a small negative voltage at gate. So what happened? Holes from the bulk accumulated at the surface. So this step is called accumulation. Okay. This step wherein we are giving a small positive voltage at the gate. Okay, and because of that, what did we achieve? Void is nothing but depletion region. So this step is known as depletion. Okay, and this step wherein we kept on increasing the positive voltage until and unless the electrons formed a connecting link between the n plus pockets and formed the channel. Okay, and the surface inverted, the surface of a p-type now has electrons. So this step is called as surface inversion. Surface inversion, and by this we have created the channel. We have created the channel. So this is it for our lecture 6, and we will be continuing from this point in our next lecture. And I wish you all a very happy new year. Please subscribe, like and comment, and if you have any doubts you can join the community or drop your questions in our comment box. Thank you. Have a nice day.